Hello everyone, welcome to my channel. In this lesson I'll be focusing on grade 12 physics and the topic is momentum and impasse. This is going to be lesson 4 and I'll be focusing on graphs. Now if you go to my YouTube channel and check the playlist section and if you check in there you find a playlist titled grade 12 physics. I have presented 3 lessons on momentum and impasse and this will be lesson 4. There's one more lesson to complete this topic. So in this lesson specifically I'm going to be looking at past exam questions. I have 2 questions to go through. I hope I can be fast enough. The first one is question 4 picked from the 2025 final exam. That's National Senior Certificate Grade 12 Physical Sciences paper 1, which is physics. It is the November 2025 final exam in the Republic of South Africa. Now let's go to question number 4, which is our target question in this one, coming from topic 1 of the physical sciences curriculum, grade 12. Topic 1 is momentum and impasse, and we're looking at this question here. So let me go through the question and please go through the question with me. It reads as follows: cricketers at an academy conduct an experiment to determine the relationship between contact time and the final momentum of a ball for a constant average net force. A cricket ball of mass 150 grams is thrown horizontally with a certain initial velocity, and it is struck by a bat so that the ball moves in the opposite direction as shown in the diagram below. The average net force acting on the ball is horizontal. Stopping this. So that's a diagram. A cricket ball projected from left or thrown from left to right and is struck by a bat at that point, forcing it to move in the opposite direction. The experiment is repeated using the same ball. That it shows you that mass is kept constant in this one. The average net force and initial velocity of the ball are kept constant. The contact time between the bat and the ball is changed each time. The results obtained are shown in the sketch graph below. So there is a sketch graph of final momentum versus contact time, delta t, in seconds. And obviously final momentum is in kg meter per second. 4.1 says define the term impasse. So we start with the definition. Naturally, like I said, it's the momentum and impasse, and this is lesson 4. So we're starting with question 1. In this one is question 4, final exam. Let's call this 2025. Let's call this page 1. Right, and 4.1 is asking us to define impasse. Here it is, define the term impasse. So we define impasse as follows. It is the product of net force acting on an object and the time the net force acts on the object. This time is also known as contact time. As you can see in the graph here, we are looking at final momentum versus contact time. That's the time being mentioned in the definition of impasse here. It's the product of net force acting on an object and the time the net force acts on the object. So that's a definition. Remember, definitions is 2 marks or no mark at all. Let's move on to 4.2, which is the main question in this one. 4.2, we are required to perform calculations. So it's calculate 4.2.1 average net force acting on the ball. Now, when you are given a graph like this and you have change or final momentum and then contact time there, it means final momentum is your dependent variable, contact time is your independent variable. Now, you remember on impasse and momentum as a topic, we have impasse momentum theorem. That's the one that connects impasse and momentum. So I'm going to write 4.2.1. The first one, we write down in-pass momentum theorem, which basically says in-pass is equal to change in momentum. Now, looking at how this question has been given, we have final momentum on the vertical axis. It means I must rewrite this equation as follows. So what is in-pass? In-pass is net force times contact time, or change in time. And this must be, remember how we write this? Normally we write M times open brackets V final minus V initial. Now we're going to say P final minus P initial. You say, why do you do that? Because we have P final on the vertical axis. Therefore, we have to write delta P in this form. And P final is on the vertical axis. That means we must make P final subject of formula in this one. So I'm gonna rewrite this. Let me repeat that because that's very serious. I'm saying if you're given a graph like this, a straight line graph, whatever is on the vertical axis, that must be made subject of formula in your equation that you're using. Now in this one, this is the equation. We have to make P final subject of formula. So I'm gonna rewrite the equation as follows. P final minus P initial is equal to F net times delta T. And therefore, making P final subject of formula, we get P final equals F net times delta T plus P initial. Now this is critical because, as you would recall, in this story here, graphs and functions, y equals m, x plus c. There is your straight line graph. This is an idea behind what we call linearization in physics. So the question is asking us to work out net force. That means all I need to do, if you can see from here, all I need to do is to work out gradient. That gives me net force. All right, so I'm going to have to work out gradient. Let's take this to page 2. Now, on page 2, remember on calculation of gradient, you need the points. So I must list down 2 points on the graph line. And the 2 points, as you can see, it's this point here and that point there. These are the 2 points. So we know the coordinates of this point and we know the coordinates of that point. So here we have 0, 0, 1, 0, because remember, y is 0 on x-axis. This point here is 0, 0, 3, 4, 5. So those are the 2 points we need. So we need 0, 0, 1, 0. And the second point is 0, 0, 3, 4, 5. These are the 2 points, like I said, this point and that point. So we're going to call this point here, this value, x1. We're going to call that value y1, just so that you remember that we're going to use the gradient formula. x2, y2. Someone says, why are you using x and y when we are dealing with momentum and time? Well, it's easier to use x and y. We know that we are on the xy plane here. Yeah, so we know we're calculating net force and it has to be in the correct unit. So we're now from here, you can see F net equals gradient. We're going to say, therefore, my average net force they're requiring me to work out must be equal to gradient M. And what is gradient? Y2 minus Y1 all over X2 minus X1. Let's perform substitution. What is Y2? Well, Y2 is 4,5. So that's 4,5 minus, what is Y1? Y1 is, you can see 0 there, all over. What is X2? X2 is 0, 0.03 minus, what is X1? 0, 0.01, as you can see, 0, 0.01. Using a calculator, this simplifies to what exactly we're looking for. Let me just use my calculator here. So what we're saying now is 4.5 basically, minus 0 is 4.5. We're dividing that by 0.03 minus 0.01. And my calculator says 225. So the net force, average net force they're asking is positive 225. And remember, force is measured in newtons. But the question doesn't say magnitude. If you check, it doesn't say magnitude. It says average net force acting on the ball. And net force acting on the ball must be to the right because the bat strikes it at that point, forcing the ball to move to the right. So we're going to say to the right here as the direction. Remember, this is a vector quantity. It must have both magnitude and direction. To the right. Right. So this is our final answer on this one. Let's look at the next question. Right. That's our final answer. Now let's look at the next question. The next question is basically talking about that one there. 4.2.2 says magnitude of initial velocity on the ball. So what are we supposed to do now? Right. What we're going to do now is the following. 4.2.2. 4.2.2. Remember now, to work out initial velocity, we need initial momentum. So we're going to take this number, put it back into this equation here, in that space. So we're saying P final equals 225 delta T plus P initial. We need to work out what P initial is. If you look at this equation here, P initial would be the value at that point, value of momentum at that point. That would be your initial. The y-intercept, remember, y equals mx plus c. Pi is c, y-intercept. So they're asking us to work out the value there first, and then we can work out initial velocity by using the momentum definition. All right, so now we need one value of final momentum and one value of contact time. Picking this point here, we have delta t equals that, and P final equals 4,5. So here we're going to say using 0,03, 4,5, we get the following. This number must go into that space, and that one must come into that space. So we have 4,5 is equal to 225 times 0,03 plus Pi, P initial. So we need to solve for Pi there. Taking this to page 3. Right, this is physics, extremely mathematical. That's why I always emphasize that physics students should always make sure that they put double the effort in maths. Physics would benefit automatically. Right, now let's move on as follows. This is page 3. So now from there you can see that P initial will just be 4,5 minus, if you multiply those out, it's 6,75. I think 225 times 0.03, the answer is 6,75, correct? 6,75. So that means P initial is equal to minus, if you subtract 4.5 minus 6.75, the answer is 2,25 minus 2,25, and we know the units of momentum, kg/meter per second. Now, if you like, we can take this back into the equation there in that space. Just to complete this, we're going to say, therefore, P final is equal to 225 delta T. You'll understand why this is important. Instead of plus Pi, we're going to put this number here, minus 2,25. So this is the equation that connects momentum and contact time. So now remember, the question is asking us to work out initial magnitude of initial velocity. We're going to say, therefore, mvi is equal to magnitude of initial velocity, P initial. If you like, put two lines like this representing magnitude. That allows us to ignore that minus sign. So basically, mass is 150 grams, which means we must change it to kilograms by dividing by 1,000. Remember, the standard unit of mass is kg. We are told the ball has a mass of 150 grams. There it is. We must convert it to kilograms by dividing by 1,000, like so. What is the magnitude of initial momentum? Is 2,25. And this is 0,15 times V initial equals 2,25. Remember, magnitude means ignore the minus sign. So what is V initial? Is going to be 2,25 divided by 0,15. when you do that, you're going to get V initial, which is what we're required to find here. You find this is 15 meters per second. The question is asking us to work out the magnitude of initial velocity. So this is the story we're supposed to have. Remember, no direction, magnitude only. So that is our final answer to 4.2.2. Let's move on to 4.3. There is 4.3. It says redraw the graph in the answer book and label it as A. All right, so we must redraw this and label it as A. Let's start from there. But let me just carry on with checking this one first, and then we'll see what the question requires us to do. Label it as A, and then it says on the same set of axes, draw the graph that will be obtained when a ball with a bigger mass is used without changing the initial velocity and average net force. Label this as B. Okay, so we need to work out, do the calculations here. Remember, this is the equation that connects P final and delta T for ball A, the first experiment. So we are going to say 4.3. Remember, these questions require you to use an equation of some sort. They will not tell you, you must just know. So bigger mass, it means we must start from here. We are starting from, so this is 4.3. This is page 4. We're starting from P final. Let me call this of A is 225 delta T minus 2,25. Remember, I told you that equation is important. There it is. But they're asking us for a bigger mass. Bigger mass means bigger initial momentum. That's the trick. Bigger mass means bigger initial momentum. So in that place, we must have a bigger value. So let's see what that means. This is the equation. Remember, the answer there will be negative. So, so for B, let's, for example, suppose M is twice the mass of the first one, which is 0.15. And what is the answer here? Multiply that by 2. 2 times 0.15, the answer is 0. 2 times 0.15, it must be I'm making a mistake. 2 times 0.15, the answer is 0.3. 0.3. So what is your V initial? P initial. P initial of B is going to be equal to mass times V initial. Remember, we're told that V initial is kept constant. But now remember, V initial, the magnitude is 15. But if you look at this number here, which is what we obtained there, this actually, if you don't ignore the minus sign, it will be negative. Why? Because the assumption is to the right is positive, therefore to the left must be negative here. Right positive, left negative. That's why here, this net force we said to the right. All right, because it came out as positive. And therefore now, we are going to use minus 15 here. So what is the mass? 0.3 times, what is V initial? Minus 15. What is the answer here? This should be minus, so that's 0.3 times minus 0.3 times minus 15. The answer comes out as minus 4.5. Minus 4.5. So we take this, put in that space. So we're going to say, therefore, P final of B must be equal to, remember, net force is kept constant, delta T, and now we have to have minus 4.5. So these are the two equations. Now you will understand why, therefore, in the sketch they are looking for, this is what we are supposed to get. Delta T in seconds, P final in kg, meters per second as a unit of final momentum. Let me just remove the dot at the top there. I'm removing this dot here, right? So this is what it should, how the graph should look like. Allow me to use a ruler here. I know these are sketches, but yeah, just for the sake of space, this is what I'm going to have. Suppose this is what I have here. and then broken line here, all the way up to down there. The other one must be parallel to this one. Why should it be parallel? Because net force is kept constant, which is gradient, as you saw. So this would be the story. It has to be solid here and broken down there. Fantastic. So now this would be A, and that must be B. Why? Because your understanding, as you can see, this would be, in case of these numbers, that would be minus 2,25. This would be minus, at this point here, you would have minus 4,5. So the graph can only be on the right hand side of this one. It's very clear from here that that's how you're supposed to sketch them. All right, so this is how you work out these things. This was the question in the 2025 final exam. Candidates were required to do what we have done in this one. All right, I'm moving on to the next question, which is question 2. I only have 2 questions in this one. I'm coming back with the last lesson, lesson 5, still going to be on graphs. That will be the last one on this topic. The second topic will be vertical projectile motion as far as physics is concerned. And if you go back to the playlist there, all these lessons are going to be in there. So you can watch them at any time you want. All right, so let's look at the second question now in this one. Just check how much calculations were involved in this one. We had to, of course, definition, there are 2 marks, and then we had to do some linearization here to produce y equals mx plus c because of the graph, and then we had to work out all those quantities required from the graph, as you can see here. All right, now let's look at question number 2 in this one. Question number 2 comes from, again, the 2025 exam, but this is the preparatory exam. As you can see here, again, grade 12 from the Republic of South Africa again, but this is from Gauteng province. And we have the final paper, November, preparatory exam, not final exam, but preparatory exam. Again, it's physics and it's paper 1. We are focusing again on question 4. Like I told you, in this video, I'm focusing on graphs only. And the next one, is going to be focusing maybe on graphs and other aspects of momentum and impasse. Let's look at this one here. Question 4. It says, Elena tests the strength of a piece of glass by dropping a steel ball of mass 5 kgs from a height of 3 meters onto the glass. The velocity time graph below represents the motion of the steel ball from the moment the Elena drops the ball until it reaches the ground. Remember, this ball is dropped onto glass, and the question says reaches the ground. It means it breaks this glass, so one has to figure it out from there. So let me do a bit of a sketch here. A bit of a sketch just to show you what I'm trying to say. And if you check going through the entire of the question, maybe let's do that. 4.1 says define the term momentum. We're going to do that. You notice now the first one is always a definition. 4.2 says calculate the net force exerted by the glass on the steel ball. Is this an elastic or inelastic collision? They're asking us to refer to the information provided in the graph to explain our answer. All right, 4.4. The glass does not break when the learner drops a soft rubber ball of similar mass. This tells you that in the initial case, the glass actually breaks. But when the learner changes from a steel ball to a soft ball, the glass actually doesn't break, and we're required to explain using the physics principles. All right, so let's look at how this is done. I'm going to start with a sketch here. So this is 2025 prep exam. This should be page, because just want to continue with the pages. We stopped at page 4. This was page 4. Now moving on to page 5. So this is page 5. And now we're looking at question 4, prep exam. Again, we're still looking at 2025. Right, question 4.1, it says define momentum. Define the term momentum. It's the product of mass and velocity of an object there, term momentum. So you just go straight and say it is the product of mass and velocity of an object. That's momentum, the product of mass and velocity of an object. Right, we're done with 4.1. 4.2, there's something very interesting that you note here. In the final exam, we had a graph. In the preparatory exam, there was a graph as well. So maybe this is an idea that says, be very careful when you're writing your preparatory exams, because they have an idea, they actually give you an idea of how the final exam is going to be structured. All right, now 4.2, it says calculate the net force exerted on the glass, exerted by the glass on the stool bore. So I'm going to have a sketch here. So a sketch is as follows. There's a stool bore dropped from some position 3 meters. So I'm going to have the ground here. So, and I'm going to have the ground, and I think I must separate these for you to be clear, to see it clearly. So let's say that is glass that's put on the ground. That's glass put on the ground. So that's your ground. And we're told that it's at a height of 3 meters. Check this, dropped from a height of 3 meters, from a height of 3 meters onto the glass. The learner tests the strength of the piece of glass by dropping a stool bore of mass 5 kg from a height of 3 meters onto glass. So height is measured from the ground. So there is your 3 meters from the ground. This bore strikes the glass. Now watch what is happening here. Strikes, dropped from a height of 3 meters. So this would be position 3 meters above the ground. The ball moves, its velocity increases obviously, and strikes the glass with that speed. So it strikes the glass here with that speed. I'm going to write it down here, indicate it that way. So that's 7,84. Now it breaks this glass, and therefore if you allow me to sketch it on the other side, because it breaks the glass, what we're going to have is the following. The ball is going to be eventually on the ground. So there is your ball on the ground. The glass is broken, one piece on one side, the other piece on the other side. So allow me to draw one piece this side here, and there's your one piece. On the other side, there's one piece there, and the ball strikes the ground. If you allow me to indicate it down instead of on the edge, because I don't have space, it strikes the ground with a speed of 1,53. Remember, we have velocity versus time. So that's, if you like, speed versus time, but in this case, there's a velocity versus time. Speed in a specific direction is velocity, you know that. So that would be the velocity with which the ball strikes the ground, which is 1,53. 1,53. That makes sense, meters per second, because the glass slows down the ball. So that's the story. Now, this is what we have. So therefore, in order for us to perform the calculation they're requiring us to perform, we are supposed to use, remember, whenever they ask you to work out net force on momentum and impulse, it's impulse momentum theorem. So we're going to say impulse, if you allow me to just go straight to F net times delta T equals delta P. Now in this case, we have velocity on the vertical axis. So therefore, it allows us to say this can be rewritten as F net times delta T is equal to M V final minus V initial. Nice. Now we can do the substitution, and we are at the answer. Right, let's move on to page 6 to maybe finish this off. Page 6. Now, what is F net? Well, they want us to work it out. So F net times delta T, the time that the ball takes to break the glass, is from here to there. So from the time it's dropped to the time it reaches the glass is 0.8. And while it breaks the glass during that period, it will be from 0.8 to 1. So delta T is actually going to be 1,0 minus 0.8 is equal to, what is the mass of the ball? We have been given 5 kgs. No need to convert it. It's already in the standard unit, SI unit. So kg, we are going to leave it that way. And then I'm going to have final minus initial. Right, let's look at what is the final velocity. Well, final velocity is the velocity with which it hits the ground, which is 1,53. So I'm going to have in that space 1,53. What is the initial? Well, the initial is 7,84 before the velocity with which the ball hits the glass. So this is F net times 0,2. If you subtract there, equals 5 times, what is the answer in there? We have 1,3, 1,53 minus 7,84. My calculator says minus 6,31, minus 6,31 in there. So work out F net is going to be equal to 5 times minus 6,31. We're dividing this by 0,2. And the answer is, let me perform the computation here. It's 5 times minus 6.31 divided by 0.2. My calculator says minus 157,75. Minus 157,75 newtons. Now the question is asking us to work out net force. Minus. Now notice something. All these velocities are positive there because we're taking here down as positive. So let me emphasize this. I'm gonna make sure I show you that here we have a plus sign, there we have a plus sign also. These velocities are positive because of that understanding. Now, so the minus sign tells us, if you like, you can say here downwards. Why downwards? Because we took down these velocities substituted, took into account the direction there. We keep that, but now the minus sign must be explained. The minus sign tells you so not actually downwards, it must be upwards. So we change that to the opposite. Remember, a vector quantity must never be left in your final step as a negative value. You must always explain it. So F net is equal to positive. We change the opposite of minus is plus 57,75 newtons. What is the opposite of downwards? It must be upward. So this is the final answer. Remember, the question does not say magnitude. It says net force. So we must indicate both magnitude and direction, as you can see here. Calculate the net force exerted on the glass, exerted by the glass on the ball. Obviously, it has to be upwards because the ball is striking the glass downwards. The glass must exert a force upwards by Newton's third law, remember? Right, let's look at the last but one. 4.3. 4.3 is asking us, is this elastic or inelastic collision? Is this an elastic or inelastic collision? Refer to the data in the graph and the relevant principles to explain the answer. Well, by looking at the velocities, there is a difference in velocity. So there's change in velocity, a decrease in velocity. So there is something important here that we need to note. For you to determine what type of collision it is, total kinetic energy must be conserved. And because velocities are different, we can't say that total kinetic energy is conserved here. So velocities are different, and therefore total kinetic energy is not the same. Mass is the same. Mass of the ball, the steel ball, is the same. Remember, 5 kgs. So same mass, but velocities are different, and therefore total kinetic energy is not conserved. Therefore, the collision is inelastic. So 4.3 is what we're looking at. 4.3. Be careful there. If you look at the marks, is 4 marks, so you have to state 4 points here. So velocities are different, therefore it means total kinetic energy is not conserved, but mass is the same. So what type of collision is this? The question says inelastic. We must choose from these two words, elastic or inelastic. So I'm going to choose inelastic. Inelastic. So that's 1 mark. The next, so in the next part here, we must say 3 or list down 3 points. 1, mass of the ball is constant. Mass of the stool ball is constant. Number 1. Number 2, velocities are different. Velocities are not the same. What does this mean? Therefore, this means total, that's the third point now, total kinetic energy, not total linear momentum. So use total linear momentum. This means total kinetic energy is not conserved. Total kinetic energy, I'm going to just jump space there because of time. Total, remember you have to say total. Total kinetic energy is not conserved. Total kinetic energy is not conserved. Those are your 3 points. So inelastic, the mass is the same, and therefore total kinetic energy is not conserved because velocities are different. Basically, I'm saying here in the last point here, this last point, if you allow me to squeeze it in this space, I'm saying total kinetic energy initial is not equal to total kinetic energy final. Remember, that's the defining condition for the types of collisions, whether the collision is elastic or inelastic. If these two are equal, elastic. If they're different, like in this case, inelastic. Why are we saying they're different? Because velocities are not the same. That's why. All right, so this is how you answer it. Let's look at the last one, and then we're done in this one. The last one says, the glass does not break when the learner drops a soft rubber ball of similar mass from the same height onto glass. Use physics principles to explain this phenomenon. Now, here, this is an application of Newton's second law in terms of momentum. You must always remember that 4.4, the last one. What page is this? This is page 7. Page 7. So to explain this, there are 3 points that you need to mark, and it's 3 marks there. Point number 1, change in momentum is constant. Delta P is constant. Point number 2, because the ball is soft, contact time is increased. Delta T is greater because the ball is soft, rubber ball. Is soft, and because delta T is greater, F net decreases because F net is inversely proportional to contact time when delta P is constant. Always say, because that's a condition. Otherwise, you can't have that without this condition. So we said it here. And when you are writing that net force is inversely proportional to contact time like that, you must say when change in momentum is constant. So this is how you were supposed to answer this question in the preparatory exam. All right, I am going to stop here in this one. Like I said, there's one more lesson coming up to complete this topic. Then I'll move to topic number 2, and so on until I complete all the topics. So you can watch these lessons at your own time from my YouTube channel now. Like I said, 3 lessons have already been presented. If you go to the playlist titled Grade 12 Physics, you'll find 3 lessons there on momentum and impasse. This is lesson number 4. There are 2 other lessons in that playlist. They are on vertical projectile motion. I've just answered 2 questions that were sent to me by a student, so you may also have a look at those. All right, tell me what you think about this. Was it helpful? I'll be interested to hear from you. All right, see you next time.